Hi there, and welcome to a video part 1 in terms of our op-amp design drills for ENEL 283. Thank you for joining me. We want to go through and we just want to brush up on some of our configurations and again some of the theory behind our op-amp designs. We're going to be reviewing some of these designs as part of assignment 2 So again, we want to just make sure that we have good familiarity and hopefully this will help clarify any confusion there might be in terms of our actual op-amp circuit designs as we're going along. So the first thing we're going to do is we're going to look at op-amp open loop characteristics. As I go here and I have an op-amp, again, when I look here, what I have is I have the two supplies. So there are my supplies. And these will range typically from anything from 5 volt to 18 volt. This is my positive supply. This is my negative supply. And we see here that we have very large resistance between V plus V minus. According to the data sheet, it's for a TLO 84. It's approximately 10 to the 12th ohms. And our open loop gain, our large scale voltage gain differential is about 200,000. So that means if I was to put in 1 microvolt on the input, what would I see on the output? Is the difference between those two. As on an output, I would see 200 millivolts, which is an extremely large gain. 1 microvolt is a fairly small signal to be dealing with, so that's what I'm looking at in terms of open loop. So the first configuration, again, we looked at was the non-inverting amplifier. Again, here we have a goal. We want to look for an input signal that ranges, if we have an input from 0 to 30 millivolts DC, that we would get an output of 0 to 9 volts DC. So again, our non-inverting amplifier configuration involves a voltage divider on the output. This is typically called R2, R1, and this point brought back, and we have Vin. Vout is equal to Vn times 1 plus R2 over R1. Again, as we go through here and we look at the analysis, what we see is that the voltage at this point here is Vout times R1 over R1 plus R2. If we look, we can see that these are actually the inverse of each other. So what this tells me then is essentially what I'm seeing here is a V out of, or a V applied here, which is V out times R1 over R1 plus R2. And the large scale differential gain of the amplifier is going to ensure V plus is essentially equal to V minus. So that gives me the performance of my amplifier. I'm going to see that in fact I have an expression where V out is equal to Vn times 1 plus R2 over R1, or if I would be more comfortable, I could say V out is equal to R1 plus R2 over R1, and that gives me my gain relationship. You might wonder, well, where does the op-amp come into the equation? It's the op-amp's open loop gain that is determining, or that is making this configuration, this relationship happen. This is the open loop gain is what's driving V plus to be approximately equal to V minus to be approximately equal to V plus. That's where the open loop gain comes into the problem. If you recall, I have the problem Vn maximum is 30 millivolts, V out maximum is 9 volts. These happen to be DC voltages, so the AV I require is 9 over 0.03 equals a gain of 300. I can achieve that if, again, I look that A sub V is equal to 1 plus R2 over R1. Essentially, that's pretty easy to achieve if I let R2 equal 300 k ohms and R1 equal 1 k ohm, that I would have my design. Now you'll notice that my actual AV is going to be 301 times, but that is a very low percentage error. That's 0.33% error in terms of my problem. So just to look here again, we have R2, R1. This is going to be equal to 300k ohms. This is going to be equal to 1k ohm. Again, my input resistance to this amplifier, or Z-in, if I want to think in terms of impedance, is approaching infinity. It's really only going to be limited by the input bias and offset currents that we've talked about. As long as we're not drawing an excess current, and remember, the rule of thumb is I max out has to be less than 25 milliamps. Dave should have given you this in the lab. So that defines my amplifier. So we've done the first one. Again, just a quick review. My second problem that I want to look at is looking at the inverting amplifier. So again, starting with our basic configuration, what we're going to see, again, here is my V out. So here is V in. I'll label this as R1. This is R2. And I will ground the positive input. Notice that my feedback for an amplifier always comes to the negative input. And here what I have is a relationship where V out equals minus R2 over R1 times V in. Now again, we went through and we looked at the nature of the characteristics of this amplifier. It's useful for me to think of this point as being a node. So when I apply V in, we'll assume, we'll make the leap of faith that the open loop gain of this op amp is operating in such a way that it's going to seek to maintain V minus and V plus at the same potential. Notice that the positive input terminal is grounded, so I'm looking for 0 volts. So in this case then, I'm going to see some current I1, which is going to flow here, and I1 is going to be equal to Vn over R1. We know that there's a very high impedance into this terminal here on the op amp. We know, despite the fact that it behaves like a virtual short, no current flows. So by Kirchhoff's current law, we know that the current that's flowing into this node N has to be matched by this current I2 flowing out. The only way we can match that current is if I2 is equal to essentially 0 volts minus V out, writing a bit of a node equation here, over R2. And we know that I1 and I2 are equal, and that's where we get our expression. So again, we see the opposite polarity output. We see the input resistance of our inverting amplifier being R1, and we have a gain expression here. Our problem that we're given says we have an input voltage from -1 to 0 volts, and our output should have a gain of -5. Again, we assume we're working to within tolerances. I'm going to add to my spec and say that Z-in should be greater than or equal to 10k ohms. Again, generally high input impedances are desirable, so that would mean that I should pick for R1 at least a 10k ohm resistor, and now I'm looking for a gain, an A sub V equal to -5. Again, this is going to be, if it's not mentioned, plus or minus 10% tolerance. What that would nominate for a resistor here would be a 51k ohm resistor. So again, my gain is close. A sub V equals minus 51k over 10k. And again, in the next example, we're going to see that we can exploit the fact that this point is at virtual ground. That's going to become very important to us. So the next amplifier we want to look at is the Summation Amplifier. Again, it's based on the inverting amplifier. We'll look at some of the big advantages we have with this particular configuration. So if I come in here and I have this amplifier, so I'll call this input A, can come down here, have input B and input C. Usually I call this resistor is referred to in Hornstein as RF. Ground my positive lead, and what I see is that, again, just if we apply superposition to the analysis of this amplifier, the current that flows here, if I call this IA, again, IA is going to flow here, so we're going to have IA. Here we have IB, and so here we're going to see IA plus IB. Here we have current IC. Again, it's added here. So our application, or the application of our amplifier, is relatively straightforward. We're just essentially, if we pick, for instance, a resistor here of 10k ohms, RA equals RB equals RC equals, say, 1k ohm, then we have a gain of minus 10 for each one of our channels A, B, and C. The beauty of this configuration is that this point is at virtual ground. So all that channel A or A input sees is this resistance here, this R sub A. All channel B sees is R sub B to ground. So we have an input that looks like this, where this is RA, V sub A coming in, and we see nothing else of this other amplifier, which is a really elegant application or appearance of the summation amp. So we've gone through a couple of examples of those. Biggest reason why we tend to look at this is for applying DC offsets. So that's where it's very important for us. We're going to look at a quick example of that. My input is a plus 5 to minus 5 volt sine wave, and what I require out is a 0 to 5 volt to plus 5 volt sine wave. So I'm going to be using a summation amplifier with two channels. This is RA, this is RB, and this is R sub F. Again, if I want to think about this conceptually, what I have is I have a block where I'm going to apply a gain. So I have an AV, and in this case I can see I'm going from 10 volts peak to peak to 5 volts peak to peak. So that's an AV of 1/2. Now again, that's the absolute value of that gain. Because I'm dealing with a sine wave, I really don't care too much about the phase. And then I'm going to have to add 2.5 volts to the signal. Now I can do that in one operation, but conceptually I want to think about it as two steps. So what I'm going to do here, I'm just going to pick a value. I'm going to pick this to be 10k. Now I need to pick RA. So this is my gain, and I want my gain to be 1/2. So that means that RA is going to be equal to my A sub V. R sub A is going to be equal to R sub F divided by the absolute value of my gain. And it's fortunate that I can get a 20k ohm resistor. So R sub A is 20k. The only other thing that I need to do is find R sub B. It would be useful if I had some supply voltages. We'll assume that we have supplies of 9 volts and minus 9 volts available. I know that if I could simply find a 2.5 volt supply, I could apply that. I don't have a minus 2.5 volt supply because the amplifier inverts. Here I'm going to apply minus 9 volts, and A sub V equals 2.5 over was minus 2.5 over 9 volts equals 0.277. That's a negative gain, and that gives me a resistor of 36 k ohms. Now, as it happens, I believe 36 k ohms is actually a 5% value resistor, so we can work with that. I'm going to stop there before I go on to the difference amplifier. I think we'll switch videos. You probably need a little bit of a break, but that should hopefully be a good review of what we'll be looking at on assignment 1. Thanks, and I'll see you in video number 2.